Welcome back. In our last lesson we looked at how to build a heart. We looked at the internal structure that we need in order to generate a high pressure system that will push blood from an area of high pressure around the body to an area of low pressure. We got it working after a number of difficulties. We end up building it, and so now that we've built it, we send it to the client that has asked for it. The problem is the client sends it back to us and the client is not happy. The client says, yes, it's a pump, yes, it goes round and round and round, but it's useless. So we say to them, well, what are you talking about, it's useless? No, it works just fine. And they say, yes, but the reason we got you to build a pump is because we need a mechanism that can bring nutrients and fluid to the cells of the body, and also something that can take it away. Your pump doesn't do that. It just circulates around and around and around, and nothing is delivered anywhere, nothing is taken away. So it was a misunderstanding. After a few more negotiations, we agreed to take the heart back. We're going to work on the entire system again, and we're going to see if we can't meet the client's needs of delivering nutrient, taking away waste. It's a little bit easier than we've let on though. At least we think so. This is what we've got so far. We've got our heart. We've got our blood vessels like that go around. This is high pressure, this is low pressure. Inside here, the ventricle, we're creating the highest pressure, and we're also creating the lowest pressure with each pump. That was last lesson's focus. So they want us to deliver something to them. They can put nutrients out into the interstitial space here. It's easy. Dop, 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 dop. Just poke it full of holes. If you poke it full of holes, then fluid should move into this gap. Now, because we're going to be losing fluid into the gap, we're going to have to top up a bit more fluid into the circulation. That's no problem. Get a bit thirsty, let's drink a bit. So we're going to put in fluid. Fluid is coming into the heart, extra fluid that we didn't have before. Now that is going to strain the heart a little bit more, because it's pumping a little bit more fluid than it had before. But hey, that's okay. So, I turn it on and all the fluid floods out through the holes, and I'm getting very minimal return through here. The blood here now is very, very sluggish. It's not going as well as I thought, at least in the experiment that I've set up. But I remember that this is going to be put inside the body, and the body is going to be constrained by the skin. Okay? So it's not going to expand out forever. If I put the barriers of, say, the skin here, or the organ that it's feeding, then the fluid will flow into here, and the back pressure generated should push it back into the blood vessels. So I devise a little experiment, I set it up, I've got all the conditions of the body, I turn it on, and the fluid just keeps moving out. This really does very, very little. We say that edema is forming, that the tissues are just basically filling up now with fluid. And again, we're getting very minimal venous return. Very minimal amounts of blood or fluid is coming back into our system. So now we know we've got a problem. We're really going to have to devise something here that can take this into account and deal with it. What we thought was going to be an overnight fix has turned into something a lot more than that. Okay. I hit the books. I'm trying to find out ways that I can keep the blood, the fluid inside here, while letting some out. I have to keep most of it inside the blood vessels and let some of it out. Well, there's an experiment I know about. It's called an osmosis experiment. Now, this is the way that one looks. In an osmosis experiment, I've got a container. I put in here what I call a semi-permeable membrane, which means it will let water go through it, but it's not going to let salt go through it. This is why. On this half, I'm going to pour in salt. So there's my salt. On the other half, I'm going to pour in water. Now what you would expect to happen is for both sides to equalize, to become the same level. So we expect water level to be something like that. But that doesn't happen. Water will always flow into an area where there's a high concentration of something like salt. That's called osmosis. What we have is this in our experiment. We have the water level on one side is a lot higher than on the other side. And that's because water has rushed in here in order to space out that sodium, that salt that I've put in there. So if I have sodium inside my blood vessels, then maybe that can hold the fluid of the blood. Now, it's going to be easy enough to get out. The pressure of the blood itself, called hydrostatic pressure, is going to push the blood out. I have very little doubt of that. But if I can load salt into the blood vessels, then it should work. So, I try. Okay, I've drawn my heart, I've loaded it with salt, I've turned it on, and straight away I start getting results. The water, the fluid, is staying inside the blood vessels. Some of it is going out under the hydrostatic pressure, under the push of pressure that I'm generating in my system, but a lot of it is being trapped. This osmotic pressure is holding blood in. Not only that, as fluid is getting pushed out under hydrostatic pressure, the amount of salt becomes more and more concentrated again. And that is going to end up drawing water back in. So it's a double whammy. Not only is it holding more water, but as the blood passes along, it's actually drawing the fluid that it's just dumped out back into the blood vessels. Now this is a pretty good system. Our pressure down here is starting to rise. Fantastic. But I'm not achieving the pressures I like. What I mean by that is I'm still using too much fluid. I'm straining the heart. This system I have given a 90-year guarantee to. But under my current calculations, the amount of work that our pump has to do means it's going to clap out in about 40 or 50 years. What I need to do is try and reduce the volume of fluid and still maintain pressure. Now, to do that, I have to look further. I have to look for something else that I can put inside the blood vessels that can hold and trap that water. And after a bit of research, I find a protein made by the liver that would be perfect for this. And that protein, quite a reasonably large protein, is called albumin. So I put albumin into the blood, I turn it on, and lo and behold, pressure is perfect. This is excellent. This is exactly what I wanted. The pressure in the system is perfect. Now this is an oncotic pressure. Albumin has a negative charge, and water will be being absorbed back into here simply to try and space out that albumin, and due to a slight charge attraction. Okay, so I think I've got it pretty well nailed. Bit of sodium, bit of albumin, punch some holes in the cells, in the walls of the blood vessel, sorry, and my system's working. I'm pretty happy. I give that back to the client and say, there you go, piece of cake, pay us our money now. And they say, yes, we can see that it's working, but does it work when we turn different systems in the body on and off? And I say, well, what do you mean? They say, well, when you're digesting, we want all the blood to go here into our guts. And when we're using our muscles, we want all the blood to go to our muscles. We need to be able to direct it. So, does your system do that? The answer is no, it doesn't. So, they give it back to us. Now things are really becoming a headache. We have to figure out a way that we can make sure that enough blood gets to the gut when we eat, when we have to digest something, and enough blood gets to the muscles when we need to use them for working out or just walking around or doing whatever. Okay, well, the immediately obvious answer is to have another blood vessel, one going to the gut, one going to the muscles or wherever you want it to go, one going to the brain, and putting that in there. So let's try it. Okay, problem solved. This one is going to feed the muscles. This one is going to feed the gut. Couldn't be any simpler, right? Now, I turn it on, my pressures drop through the floor. Why did they drop through the floor? Because I need more fluid. I've now got a different system here. Okay. So I top up our circulatory system with more blood, thereby increasing the load on our heart. But that's okay. Two systems. Let's see if we can get this thing working to begin with. I've added it. I turn it on. The heart is beating. Blood is going around to the gut and to the muscles. This is working just fine. But the strain on the heart is starting to take a toll. I'm getting readings that I don't like. There's no way this is going to live up to a 90-year guarantee. I need to reduce the stress on it again. So it's not just sodium, it's not just albumin, there's something else that I need to do to reduce stress. Okay, here's one thing I've noticed. That when I eat and I start to digest, that is putting a strain on the heart. The heart rate is increasing, stroke volume is increasing, which means the heart is even squashing harder, try and get the blood around, but I'm also getting a bit of a pump in my muscles just from eating, which is strange. Similarly, when I'm doing a workout and I want all that blood to go to my muscles, I feel it going to my gut and I feel a little bit bloated. So if I could somehow switch the blood so that when I want it to go to the gut, it goes to the gut. When I want it to go to the muscles, it goes to the muscles, then I'd be onto something pretty good. Okay, to figure out how to do this, I need to go right back to the very structure of a blood vessel. Look at what I've got to play with and how I can build this in. What I'm going to try and develop is some type of a switch that I can use. So, here are the building blocks for a blood vessel. I've got tiles. The inside of the heart, the inside of all the blood vessels are lined with tiles. Now, if you think of running on wet tiles, just how slippery that can be, that is the purpose of these tiles, to make the blood vessels very, very slippery. So the innermost lining, blood vessels of the heart, are these tiles that we call endothelial cells. I can't really do a lot with those. Okay. What else have I got? I have muscle, rings of muscle that I can slip over a blood vessel and make them contract. So contracting rings. And lastly, I've got some elastic tissue that I can play with, like elastic bands. So elastin. Now, by playing around with this, I should be able to come up with something for the entire circulatory system. Now we're getting into some heavy stuff for our client. This is what I devised. I've looked at the entire circulatory system from point of exit of the heart all the way around to where the blood vessels go back into the right atrium. Now, the first part of the heart, the aorta, I'm going to load with elastin. Now, rather than thinking of it as elastic bands, which is very soft and springy, I want you to think of it as hard rubber. If you think of rubber that is really hard to push open, imagine the recoil when I take the pressure away from the inside. It just bangs shut. So I know the heart is generating the most pressure of the entire system. So I put just enough elastin there to make it thick and heavy so that when that blood is pumped into the aorta, it stretches open, but then just contracts very, very powerfully. And that will propagate blood along the blood vessels. And I know it will do that because the one-way valve there, aortic semilunar valve, is shut and locked. So there's only one way for it to go, and that's going to be down the blood vessels. So, now in my system, my blood vessels are branching, and I have to try and maintain pressure. So what I'm doing is I'm decreasing the diameter of the pipes. And just like putting your finger over a hose, when you decrease the diameter, you increase the pressure. Of course, when it comes spurting out. So by decreasing, controlling the diameter of my pipes, I'm controlling that pressure. Now, as the pressure does inevitably drop, this elastic tissue becomes more of a hindrance than a help, because it doesn't have the strength to open up the blood doesn't have the strength to open up that elastic tissue and to force its way in. So if anything, the elastic tissue is now slowing it down. So I start backing up, start taking out that elastic tissue. I don't need it as much anymore. And in its stead, I'm going to start putting those rings of muscle. What they can do is they can mimic the effect of that elastic recoil, because muscles will contract. So as it comes along, the muscle is going to contract as if it's elastic tissue and force that blood through the system. So that's pretty good solution to the problem, I think. Now, as we get closer and closer to where we want the blood to go, we reach a point where we lose all of the elastic tissue, our muscular tissue becomes a lot thinner as well. And then we actually reach a point where we've basically only got those tiles left. And they're those endothelial cells, and that forms what we call a capillary bed, a little network of like tiny roots that are all intermeshing, and through which the blood is going to be leaving. And it's in these capillaries that the hydrostatic pressure is going to be able to force its way out, force the fluid out, and that the reclamation through the colloid osmotic pressure is going to be able to suck back in all of those fluids that it needs to retain blood pressure. Now, one thing I can do at this point is, where I've got these muscles acting, I can be a little bit clever. I can say, okay, let's not just act like the elastic recoil. Why don't we selectively constrict some blood vessels and selectively relax other blood vessels? That would have the effect of changing the diameter of the pipe. Now, we said that here the diameter of the pipes are getting smaller and smaller as we go along. Now we can voluntarily control it. So if I constrict this blood vessel here, that means it's going to be creating a higher pressure inside it. The fluid in there will be under a higher pressure. Most of the fluid will be directed towards a lower pressure, because fluid likes to move from high pressure to low pressure. It will always choose the lowest pressure it can, the path of least resistance. And so I can get blood to go into the blood vessels that are relaxing or are not as constricted. So I call that vasoconstriction, and the other one I call vasodilation. That is one way that I can shunt blood between the muscles and the gut, and it's a pretty good way of doing it. Now, I test it. I turn the pump on. It's working well. The whole system, the albumin, the sodium, the hydrostatic pressure, the muscular arteries directing blood here and there is working well. It's working almost like I want it to, but it's not quite where I need it to be. There's still too much strain on that heart, and honestly, I'm still losing too much fluid into the intercellular space. There's not much I can do about that I know of. I think I've tried everything with sodium and albumin. So I've got really two issues there. What I can do, I've just realized, is in the little blood vessels just before the capillaries, I can be very, very precise, and I can constrict those. And in effect, I can use them as little taps. These blood vessels here that are not capillaries, these little arteries, which are called arterioles, can constrict. Now, it may sound like a tiny little who cares type thing, but if I've got 5,000 arterioles all constricting, then within the organ I am supplying, I can direct blood flow. I can reduce the demand. So for example, if I'm working my arms, I don't need blood to go to both my biceps and my triceps if I'm only working my biceps. So by shutting off the arterioles, or shutting down, reducing the diameter of the arterioles, so on the tricep side, I can control the blood. Therefore, the fluid demand needed to fill this entire circuit is less, because I'm not using as much fluid. Does that make sense? Let's see. Okay, here's somebody's arm. Now, to do an arm workout, namely to work the biceps, I'm going to need 2 liters of fluid. The problem is that if I can't control the blood flow to the arm, it also means that I'm going to need 2 liters of fluid here. So I'm going to need 4 liters in total in order to get 2 liters in the area I need it. If I can shut this off, I can still get 2 liters here and save myself 2 liters. So I've reduced the fluid demand of the circulatory system just by controlling those little tiny taps, the arterioles. Now, as an engineer, I'm a perfectionist, and even though this system is really good, I'm still not happy with those numbers coming back. I can give you about a 70-year guarantee on the heart, but I can't give you that 90. I can't give you that extra 20 years because those numbers are still higher than what I had originally. And I want it to be perfect. I want it to be exactly what I gave you the first time and meeting these extra demands of the body. So after thinking about it long and hard, I come up with a solution. Well, first of all, I'll tell you the problem. The problem is that I'm still getting too much edema in my tissues. There's still too much fluid moving out of the blood vessels into the tissues, despite the sodium, despite the albumin. Okay? The colloid osmotic pressure is not as much as I want to draw it back in again. So this is what I do. Here's our circulatory system. Here's our capillary bed. Little arterioles on this side, little venules on this side taking up the blood. I'm going to start a whole new blood vessel, a vein here. So it doesn't begin with the heart. It's not part of that system. This blood vessel's sole purpose will be to collect that fluid, that excess fluid, and be like a vacuum cleaner. just sucking fluid out of the tissues all the time. And then eventually I'm going to hook it up with the veins, and it's going to dump back into that. Now I'm going to call this vessel, I can't call it a vein, because a vein kind of implies it's part of the artery venous system. So I'm going to call this a lymph vessel. Now, I'm very impressed with myself. I turn it on, I test the system, those levels drop. The amount of fluid I need to get this operational is good. It's back where I want it. I can give you a 90-year guarantee. Now, I go show my mate who works down the hall. He's an immunologist. He comes, he looks at my system, he says, well done. He goes, but I've got an idea. We're working on something down here in immunology that's a bunker of immune cells. What about if we put these bunkers along your lymph vessel? I mean, you don't have to worry about interrupting the flow of blood, because really it's not on the arterial side, and it's not going to affect the rate of venous return, because this is a vessel unto itself. So let's load it up with these little bunkers. I think that's a wonderful idea. So these little nodes that I'm putting along the length of the lymphatic vessel are called lymph nodes. And they're going to be loaded with immune cells, B cells, T cells. And effectively what they're going to be doing is sampling, tasting that fluid that is being sucked out of the tissues. And it's a fantastic way of actually detecting very quickly where there's a problem, where there's an infection in the body, where something is going wrong and proteins are being broken down, things that shouldn't be there, toxins or whatever are appearing. So wow, what a bonus for my client. I hand it to them, they seem happy, at least for the moment. They're going to have a play with it and get back to me. Thanks for listening.